Thanks so much for the invite. I'm very happy to be here as well. This is kind of like a last-minute talk preparation, so I welcome questions throughout the talk. It's not clear or anything. This is work I've done with some collaborators, Gaetan Barbe, who's an immunologist at Rutgers, New Brunswick, Moshe Silverstein, who was a PhD student at NGIT with me, and Pedro Villanova, who's at Stevens Institute of Technology. Okay, so we have some papers. First one's kind of under review, should be accepted soon, I believe. And I've got a second paper here, which is published. So I'm going to be talking to you about stochastic calcium waves. Calcium's kind of like a ubiquitous thing in biology. You can't avoid it. It's one of the most studied phenomena by mathematicians in biology. I'm interested in calcium waves in an immunology context. So we're going to look at what happens when immune cells bind to bacteria. So it's a complicated process, lots of things go on, but basically what happens is that various signaling molecules are released by the bacteria, and that'll trigger calcium waves throughout the cell. So calcium waves are these space-time organized patterns of calcium that sort of increase intensity, then decrease in intensity throughout the cell. And I'm going to try to reach a mathematical description of these waves. Okay, so as I was saying, you can't really avoid calcium if you're reading mathematical biology. Okay, there's many textbooks on it by Jim Keener, more recently by Sneed and Falke and co-workers. It's a quintessential example of what we call an excitable system in mathematics, meaning that there's often fast activation. So there's like a threshold that you have to get beyond for it to activate. And then you have like a burst of activity once you get past that threshold. And then you have slow subsidence back to equilibrium. So mathematically, it's kind of like neurodynamics, if you look at like the Fitsu-Nagumo or the Hodgkin-Huxley model. It's also inherently multi-scale, okay? So there's many things that work in this process. You have microscopic calcium channels throughout the cell. These are very small, and there's many of them. You have these individual calcium molecules that are diffusing throughout the cell. But the wave itself is very much a macroscopic thing because there's an organization going on. Enough of these channels have to open, and if enough of them open, then that'll sort of encourage more calcium to leave the endoplasmic reticulum, which will then spread throughout the cell and then open up more of the channels, and then that'll in turn lead to more calcium coming in and then more channels opening. So you kind of get this feedback effect where microscopic stochastic events, so individual channels opening and closing, can kick off large-scale waves that spread throughout the entire cell. So it's inherently multi-scale. It looks stochastic, okay? It never looks the same twice. So it's kind of this interesting thing where you have this organized, beautiful space-time patterns coupled to stochastic phenomena. We want to sort of reach a description of how this can happen. I'm primarily building off the experiments by Gaetan, but let me emphasize, these sorts of waves happen all over biology, not just in immunology. Okay, so at the top, I've got like a calcium fluorescence of what it looks like. So all he's done is he's, if you will, taken a picture of the cell over time. So you can really see how you have these space-time patterns and it's evolving in time. So it's it'll sort of build up in one area. You'll see it'll be white, for example, and it'll subside and then build up in another area, then subside. And if you plot a time series here in red, so if you look at figure B, that's the individual time series, you can really see that it looks like it's spiking. So it really kicks up throughout the cell, then it will subside, then it'll kick up again, then subside. So it's got this sort of oscillatory looking spiking behavior. In figure A, he's plotting the average over many time series. Okay, so when you average over many such oscillations, you don't see the oscillation. But we're just emphasizing here that after stimulus, calcium activity is on average much more than if there is no stimulus. Okay, any questions so far? Okay, so classically, people prefer deterministic models for this sort of thing. So if you go to Keener's textbook, he'll look at ODE models where you have sort of coupled ODEs. For example, this is calcium concentration, and then P is IP3, one of the signaling molecules. And it was proved that this basic set of ODEs will support an oscillation. So if you choose parameters that are in a sensible regime, you'll get a Hopf bifurcation and you'll see an oscillation. Okay, so that's sort of was the most popular explanation for many years. But more recently, a lot of people have come to think that maybe a stochastic description is more appropriate. There's various reasons for this. If you just look at the time series or the calcium fluorescence, it's not the same every time you look at it. So it's going to vary a lot. It'll vary in frequency. It'll vary in the actual positions of the waves. It looks sort of stochastic and bursty, like most things in biology. And one of the biggest proponents of this view is Martin Falke, who I've referred to next. He really looks at the time series for the spiking, and he'll really argue that it looks Poissonian. Okay, so if you take the ratio of the average interspike interval to the variance, that corresponds to the Poisson distribution. So he really thinks it's stochastic, and that's actually become the dominant view, that this is an inherently stochastic spiky phenomenon. So the big challenge then, of course, and I'm quoting here from the textbook here by these guys, given that we're seeing this stochastic behavior, can we sort of describe this mathematically? Can we describe how microscopic stochasticity, the individual calcium channels opening and closing randomly, can sort of self-organize to lead to these cell-wide calcium waves? How does this sort of periodic organized behavior come out of the stochastic phenomena at the microscopic level? Okay, so as I said, it's inherently hierarchical. We're bridging scales. We're trying to understand how individual channels opening and closing microscopically at the 10 nanometer range can then lead to local puffs. So what happens is you have individual blips, if you will, of individual channels opening and closing, which will then, if there's enough of them in one area, that'll lead to a puff where you have sort of a local cluster of channels that open. That's in the middle figure. And then if enough clusters open in some area, then you'll get a cell-wide wave. So we want to understand this mathematically. So with my student, we did something very naive to start with, because we're just starting out. So we say, well, let's fit a curve to the interspike interval. Okay, so we have here a histogram of the range of interspike intervals that are observed, and then he fits various gamma distributions. Okay, if we only saw an exponential fit here, then we would think that's just a thoroughly Poissonian phenomena. Okay, if this was a pure Poisson phenomenon, then the interspike interval, that would be the exponential distribution, and you just get a beautiful exponential decay here. Okay, but we don't quite see that. The exponential fit, the pure exponential decay, doesn't fit very well. And if you just try to fit for a few more parameters, okay, you take a more complicated gamma distribution, you can really see that there's more timescales at work. Okay, so there's, as a first approximation, it may look approximately exponential, but then you have these additional decay terms, and that's telling you that there's extra timescales at work, there's extra processes at work other than just simple exponential opening and closing of ion channels. Okay, so we want to do something a bit more complicated. So like a true mathematical biologist, those of you who worked with Breslov at Utah, I tried a piecewise-deterministic-Markov process. It's very popular in certain quarters. So this is kind of a sensible choice if you see a stochastic process in biology with multiple timescales. So if you have something that's flipping stochastically randomly, okay, so you have a stochastic component, and then you have ordinary differential equation components that evolve deterministically, and they're coupled together. So the flipping of the stochastic process, that'll depend on the ODE, and the ODE evolution will depend on the stochastic process. So this seems like a sensible choice because we want to say, well, this is still a very crude model. Let's take, as a really simple model, let's say that it's either open or closed, which is really simple because obviously there's many such channels. This is kind of like just an aggregate. On average, are they open or closed? That's the stochastic variable. And then the deterministic variable is the calcium concentration. Okay, so the rationale here is the calcium's going to reasonably quickly reach an equilibrium relative to the channels. And so we can approximate that as an ODE. Okay, so I've just lifted a standard ODE model for calcium dynamics out of the textbook. I've coupled it to the opening and closing channels, and I'm going to try to reach a description. So naively, what we can do is, well, we can say, let's firstly just see what this looks like in equilibrium. So we're going to take the Fokker-Planck equation that corresponds to this. We're going to set it the derivative in time to 0. We're going to find the equilibrium distribution. We can solve for all that, and then we can fit that to the data. And it's a reasonable fit. So this seems like a good class of models to be using to study it. But again, it's still simple because previously I said the channel state is either 1 or 0. That's very crude. Okay, there are many channels, at least 100, if not more, typically throughout one cell. So let's now try to develop a proper microscopic model. We're going to have n channels, take n to be typically like 100, which is pretty big relative to these scales. Let's take them uniformly distributed throughout the cell, and then couple that to a calcium that's also diffusing throughout the cell. Okay, so these channels are opening and closing randomly. Their rate of opening and closing depends on the ambient concentration of the calcium. And I'm taking a simple model of calcium still because I don't want to make it too complicated. So ideally, calcium should be a PDE. Okay, we have a spatial structure to the cell. Just taking it as an ODE, just taking it to be uniform throughout the cell. Not perfect, but it's a good start. And now I'm going to analyze this model and ask the question, how likely is it that enough of these channels open that you see like a big elevation in the calcium concentration throughout the cell? Okay, so I've plotted here to some simulations. This is kind of anticipating where I'm going. So in the blue is just, and the gray, that's just multiple simulations overlaid. Okay, so on the y-axis here, this is the fraction of open channels. I think n was about 100, so you should see that going up by 0.01, or give or take. I'm not sure exactly what he shows there for n. But the point is, it looks very stochastic, but over time, enough of them, you can have rare events such that enough of them will open that you'll see suddenly a spike in the number of open channels. So it's superposed with, so red is going to be our predicted asymptotic for the number of open channels, which I'm getting to next. Okay, so I want to, as I said, estimate the probability of enough of these channels opening that you get a cell-wide event. Okay, so I'm going to use large deviations. It's still kind of relatively underdeveloped for piecewise-deterministic-Markov-Processes because these haven't really been used so much historically compared to other, like diffusion models, much more popular. But partly thanks to Breslov and others, they are becoming more popular in mathematical biology. So we firstly proved a large deviation principle for piecewise-deterministic-Markov processes. What this is, it's just an asymptotic estimate for the probability of rare events. So it's not exact, of course, it's an estimate. You're just trying to get the leading order estimate for how likely a rare event is. And these rare events scale as e to the minus n. So remember what n is? N is the number of calcium channels. So the bigger n is, obviously, the less likely rare events are. And that kind of makes sense because the more channels you have, the harder it is for something significantly different from the average to emerge. Okay, because like with everything in probability, if you take enough random events, take the average, with high probability, what you observe is like what you expect. So it gets harder and harder to see something rare, and we're just trying to estimate if something rare was to occur, if enough of these channels were to open that you have a cell-wide wave, well, what would be the trajectory followed by the system in attaining that cell-wide wave? So what we have to do is we have to try to minimize this rate function j. This is sort of the coefficient of n. So if you just look at this naively, the smaller j is, it's always positive, but the closer it is to 0, the more likely an event is going to be. So what we're going to do is we're going to say, well, we want to start from equilibrium. We want to attain a state where most of the channels are open. So given those two endpoints, what's the value of j that will minimize, what's the value of sigma and c? So what's the path that will minimize that function j in attaining those two endpoints? So it becomes a constrained optimization problem. Okay, so I don't want to go through all the details, but because we have a piecewise-deterministic Markov process, remember I said there's a stochastic component and a deterministic component. So the deterministic component, that sort of manifests as a constraint. So that's what the second integral is there. I've got a Lagrange multiplier. okay? Because I'm just assuming the calcium evolves deterministically according to an ODE from the textbook. So that's always got to be the case, no matter what happens to the channels. Okay, so that's my constraint. And then the first integral, that's my Lagrangian, which I want to minimize. Okay, because minimizing that corresponds to maximizing the probability. And as I said, I have two boundary points that are fixed. So I've got to minimize J relative to those two boundary values. Okay, and I just, I don't want to go heavy on the equations, so I'll try to give you an intuition for what the Lagrangian looks like. So if you just take a really standard Poisson process, okay, so this is a process that will increase by increments of 1, and the probability of an increase happening over a small time interval just scales as the width of that time interval. Okay, and now if I rescale this, so I take a long time, scaling with n, and then I divide by n. Okay, so if you take n to infinity, you know what this is going to go towards. It's just going to go to yn of t equals t. It's just going to go increasing. But there is a probability of a rare event, a deviation from the expected behavior, and you can estimate that. I'm not going to go through the details, but what you do is you get that your rate function is this function L at the bottom. So it's z log z minus z plus 1. It's got a unique 0 at 1, otherwise it's positive. So basically, to prove our result, we take this theory and we kind of do like a transformation to the homogeneous case to get our rate function for the inhomogeneous case. Okay, so I'll just make some comments here. We didn't love our numerical results for the largest deviations for this model. Again, unfortunately, it's still too simple. Okay, so what we found in particular is the calcium didn't change very much. So it just changed very marginally from equilibrium to hitting that threshold, and that didn't seem very realistic. And it seems that we need to develop a more complicated model which takes into account the spatial distribution of the calcium channels. Okay, because when some of these channels open, it takes time for the elevated calcium concentration to spread to the other channels. Okay, so there's space-time events that are going on, and there's a time lag that is necessary in it spreading from one place to another, and our model needs to take that into account. So we need to have a PD for the calcium dynamics. The other issue is what I call the robustness problem for large deviations. So large deviations estimates in biology, they're of the form e to the minus n times a constant. The issue here is that if you misparameterize just by just a little bit, you get something that's completely wrong. Okay, because if you take j of z is 1 as opposed to jz equals 2, well, if n is 1,000, there's a massive difference in probability between those two events. It's e to the minus 1,000. So it's very, very sensitive to parameters, the rate function, and it's very easy to get an estimate that's incorrect. So I think this is a real issue. And I think it makes it hard if you want to apply large deviations to biology, because it's generally thought that a lot of these biological phenomena are robust. They occur reliably. They're not completely haphazard. So if it's really sensitive to parameters, it makes me think there's something wrong with the model. How much time do I have?
Well, you have 6 minutes.
Okay. So probably won't spend too much on this, but so this is just explaining how I get the Lagrangian for my rate function out of the homogeneous case. I told you that little l, that's the rate function for the homogeneous case. So as I said, all you kind of have to do is you have to rescale it. So I just take the standard rate function, and I'm rescaling by the reaction intensity for both open to closed and closed to open. That's roughly how I did the proof. So I think my slides are slightly out of order here, but so this is another result I had. So again, I'm overlaying the large deviation prediction with the stochastic simulations. Okay, so in light blue, we have the overlaid just many random simulations. And then in red, I'm plotting the path predicted by the theory. Okay, so I've solved that constrained optimization problem with the two endpoints. So the theory is going to give you a smooth solution. And then in blue, what we've done is we've conditioned. So we've taken the simulation, we did many such simulations. We took one that finished close to what was predicted by the theory. So we just chose one of the simulations that's close. The final value is close to the theory, and the first value is close to the theory. And you can see that the path does look very much like what the theory would make you believe. So just to explain again what the theory is doing, it says given the constraints, so given where you finish and where you start, it's giving you the most likely trajectory followed in connecting those positions. So indeed, we're seeing that the most likely the trajectory that was closest to endpoints does indeed look like what's predicted by the theory. Okay, so this is just hinting at how we went about the proof. We just took the homogeneous theory and then we rescale in time, and that gives you the inhomogeneous large deviation principle. So as I said, the homogeneous case is not the most realistic. We want to have a spatially distributed model, and that's indeed kind of clear when you look at his experimental data. Okay, these waves, they're not homogeneous throughout the cell. They've got a real spatial structure, and if I had a video to show you, you'd really see that it's slowly diffusing throughout the cell. Okay, it's a space-time process. So we really want to have a PDE for the calcium concentration coupled to a spatially distributed model for the channels. So for our next work, which is still ongoing, we take a very simple ring domain. It's not a cell, obviously, but it's a 1D approximation to a cell. And we have our channels distributed throughout the cell. Again, they're opening and closing randomly, and we're going to try to derive a large deviation principle and predict the shape of the calcium wave. Okay, those of you who've read the literature, this is kind of like the diffuse fire model developed by Joel Kaiser and Greg Smith in the 90s. It's been developed further by Jim Keener and Steve Coombs, amongst others. So the idea is you have these discrete channels that will release calcium, okay, coupled to PDE for the calcium concentration. And the channel model is still the same as before. So they're still just very simply flipping between being open and closed according to intensities that depend on the ambient calcium concentration. Okay, so if I was just to take n to infinity, take many, many such channels, what would I get? Well, I'd get a continuum model where you again have the calcium concentration, and then instead of individual channels, what I'd have an ODE, which gives you the proportion of open channels at a particular location. So that's what the second equation is. It's just sigma is just proportion of open channels at position alpha and time t, and it's now just evolving continuously according to the reaction intensities. Okay, so again, we want to do large deviations. We want to predict rare events relative to this. So if n is not asymptotically large, what happens? Can we predict these space-time waves as seen in the experimental data? So you get a more complicated rate function. It's now spatially distributed. We're currently trying to solve this. I don't really have nice numerical results, unfortunately. It's just hard because, as many of you know, this is a non-convex optimization problem, and there's not really much theory for how to do this. So we've got ongoing work. We kind of get some solutions, but we're not that happy with them. It's ongoing. Yeah, I'm currently working on developing the means to do this non-convex optimization to more accurately match the data coming from the experiments. And there's all sorts of things I want to do in the future to develop this further. You can always make it more complicated. Those of you who work in biology know this. I can have more types of channel, more types of signaling molecule diffusing throughout the cell. And as I said, I want to get away from this extreme sensitivity of the results on n, because that doesn't seem very realistic to me. Okay. Well, thanks again for listening, guys, and for the invitation to give this talk. I've got my collaborators here I want to acknowledge, and we've got papers under review. Thanks again.
Questions for James? Yeah, Dennis.
have a technical question about the spatial case in the model.
Yep.
In the equations that you showed, you consider the influx of particles as kind of integral term. But I would rather expect the boundary go introduced for the boundary condition. Is it equivalent or is it not? Or can you comment on that?
It's an influx of you mean so there's two things. Do you mean the calcium leaving the through the
the effect of calcium channels?
So we naively in this model. Let me go back.
Previous one. Yeah. This one.
So the idea is, so you mean the right-hand term in the calcium PDE. So the idea is, if a channel's open, then there's a function that stipulates how much calcium will leave through that channel.
So this is in the bulk. This is inside the cell.
In the bulk, yeah.
The point source is on the boundary.
That's right. Yeah.
So I think some of the things that we might expect is that in the end of the day, if you take the correct limit, you get it changes the boundary condition on C.
That's
bringing an integral term in. I think that's.
So what you'd expect? What would you expect?
A Robin site boundary condition or something on C.
Okay.
What are the boundary conditions on C?
So I haven't actually done the proof of that.
Okay.
So I've done the large deviations. I'm not certain, but that looks correct to me.
I've got other
I'll have to talk to you. I'll talk to you later.
More conceptually. So you said right at the beginning that there's these classic models that are basically coupled ODEs, nonlinear ODEs, right? And they don't generate oscillations, or they can. But you could take the simplest one I know is the Schnackenberg. You can simulate the two ODEs, and they just go to an equilibrium. But if you simulate them stochastically, it's like, all right, these are actually do a Gillespie simulation to simulate ODEs. They generate spike trains. So is there a sense that actually a simple model can predict this, but it's just the fact that the biology implements it stochastically rather than as an ordinary differential equation.
That's a great point. So just to be clear, I'm not sure I explained correctly. So the ODE definitely can support oscillations. It depends on how you choose the parameters. So that's all in the Keener textbook. But no, you're right. That's a great point, and that's certainly a viable way to go about it. So you could just say, take my ODE, and then, if I understand you correctly, force it by stochastic spikes, and you'll see. It's kind of like the forced Pitsu-Nagumo model, right? So you'll see the stochastic spikes. Yeah, I mean that's certainly a viable thing to do. Yeah, and absolutely. That's something we probably will do in the future.
Okay. Any other questions? Oh, there's one question up here, please.
So I'm not entirely familiar with the language, but is this a non-convex optimization problem because there exists no specific global or local optimum?
It's just it's just the function. So the rate function that depends non-linearly. It's non-convex in the path that you're trying to find the minimize with. So it's non-convex in many ways. Let me go to this horrible thing, because so you're trying to ultimately solve for sigma and C, right? And lambda is nonlinear, okay? And then L is also nonlinear, and it's spatially distributed. So it's just I don't see solving this. It's not straightforward. If you talk to those who work in large deviations, most people, there's no known way to nicely minimize these spatially distributed rate functions. I don't know of anyone who has a good way of doing it that works really well and it's really quick. It's just in general because it's just too nonlinear and there's too many variables. Happy to chat later.